Okay, so without any further delays, let's start with a brief summary of first lecture 2 days ago. It's about the new no-hair idea, which was proposed in '71 in a more concrete form. It's based on a number of results in electrovacuum, Einstein gravity, on some uniqueness theorems that indicates the fact that black holes are very special. That means, to give you a brief summary, if you have, for example, Q stars or any normal objects without a horizon, solitons, with the same mass and angular momentum, they could be very, very different. All kind of quantities extra apart from this mass and angular momentum, which are different, quadruple and so on. But if you have two black holes, according to the no-hair conjecture, same global charges at infinity, they will be automatically the same black hole. Just a kind of amazing universality. So it means the black holes should uniquely be characterized by their mass and angular momentum and possibly electric charge, something subject to a Gauss law measure at infinity. Okay, so this was the expectation. It holds in electrovacuum, Einstein gravity plus Maxwell field, asymptotically flat in 4 dimensions, and the expectation was that it should always hold. This is the spirit of the no-hair conjecture, but one has to do a study case by case. Simplest case, of course, is Spinzero scalar field. There are various no-hair theorems, and here we summarize set of 3 basic assumptions, implying that there are no black holes with scalar hair. So first assumption was that the scalar field has a standard kinetic term, normal standard usual kinetic term. The second one was an assumption about the potential, and finally the third one is about the symmetries of the scalar field, which are similar to space-time. And you can find more details in this review work, but all these 3 assumptions can be violated. We have seen during first lecture 2 days ago some details on these violations. For example, the first one is the Einstein scalar model, simplest counterexample with a quartic kinetic term for the scalar field. But in a model with 4 scalar fields, real scalar fields subject to a constraint. It's the scalar model used in particular in nuclear physics or in condensed matter. But it possesses also hairy black hole solution, but this is rather exotic for us. Second one implies a violation in the end of the energy conditions. You typically have negative energy densities, so a kind of anti-gravity supported by a particular feature of the scalar potential. You have hairy black holes in such models, even exact solutions if you like, but this is again a very artificial model. You have to accept some large deviation from standard physics. And finally, at least in this very simplified picture, there is another assumption that the scalar field inherits the space-time symmetries, which also can be violated. And this results in black holes with scalar hair again. But this time, the deviation from standard physics is rather minimal, so because we use a usual, normal, complex scalar field, no higher derivatives, no self-interaction. The self-interaction can be added, but it doesn't change anything. What we need is just a mass term for the scalar field. So this is perhaps the simplest field in nature. And if you assume that the scalar field possesses a specific dependence on the azimuthal angle phi and an harmonic time dependence, then you find hairy black holes. In this case, this is perhaps one of the most natural violations of the no-hair conjecture. And as I said, this is a natural model, could be relevant in astrophysics. Here, the mechanism behind which I shall describe in a while is more general. Such configurations were generalized for spin 1. Again, we have a vector field, complex vector field with a mass term, so a Proca field. And one finds a very similar set of solutions, hairy black holes. There are no results yet on spin 2. It's an open problem because even conceptually the things are more complicated, but such configurations are likely to exist for any bosonic, any spin of bosonic field. In both cases, the field should be complex with a specific dependence on phi and t, on angle phi and time t. And it should possess, however, a mass term. This is mandatory because we need some confining mechanism. We don't want radiation at infinity. That's the only reason. But I emphasize for other asymptotics, we don't need it. In particular, in ADS, which is a kind of box, there are such solutions without a mass term. Now, I have a few slides about the properties of such black holes. They were already mentioned in a few talks last few days, so I shall be rather brief on discussing their basic properties. There are two complementary viewpoints on introducing such configurations. One may, they possess first a solitonic limit. You have a zero horizon level, a zero horizon limit of the black holes. The configurations do not trivialize, they become spin zero or spin 1 boson stars, scalar or Proca stars. And in each case, one can add a tiny black hole at the center and so on. Or there is another perspective starting from Kerr vacuum black holes, where you find a branching of these vacuum solutions towards a new family with hair, scalar or Proca hair, because of superradiant instability. And there are such a picture, it is useful to start from the direction of superradiant instability by solving for Spinzero, the Klein-Gordon equation in a Kerr background. One can repeat the same for a Proca field. And it's nice, we have even exact solutions in a limit of extremal black holes. Otherwise, we have again the Hoyne equation, which has interesting properties, but it's not very useful on this context. You cannot do too much analytical work, despite the presence of formal presence of an exact solution. But for extremal limit, there is just a Legendre polynomial or something like that. Now, we have this superradiant instability process, which was mentioned in a talk yesterday, or two talks even, which was known already in the 70s. It's the wave analog of the Penrose process, the scattering waves for a massive field, in our case, on the black hole horizon. And the solutions of interest are just at the border between, so in general, frequency will possess an imaginary part, which can be positive or negative, depending if it's growing or is absorbed by the black hole. But our solutions of interest will possess a zero imaginary part. So this will describe some clouds, stationary clouds around a Kerr black hole. The wave function is normalizable. It has all desirable properties. It's a bit like hydrogen atom in quantum mechanics. And then we have these clouds which ignore the back reaction, are just the seed of the hairy black holes. The hairy black holes, if you like, will be the back reacting version of this linearized clouds around the Kerr black hole. And then we have a specific relation between frequency, azimuthal winding number m, which appears in the phase of the field, and the angular velocity at the horizon of the black hole. So that emerges naturally in a very rigorous way when studying the properties of the wave equation, Klein-Gordon or Proca. Okay, so I shall not enter into details about the numerical construction of such configurations. I think George will give more details tomorrow. It involves solving a set of elliptic partial differential equations. There are no analytical results, unfortunately, beyond this closed form expression of the clouds in one limit. But at least for the Spinzero case, there is an existence proof given by mathematicians in this preprint. It's published. So, and such configurations were reproduced by many other groups independently. So they should exist. Now, they have a variety of very different properties than Kerr or Kerr-Newman. They are a kind of counterexample to everything we knew before for a rotating black hole. So first, perhaps counterintuitive, they do not possess a static limit. So they are not connected to Schwarzschild black holes. It's very different. Then they can violate the Kerr bound. So for Kerr or Kerr-Newman, we have a maximal value for rotation. Here, this rotation parameter, the ratio between angular momentum and mass squared, can be extremely large, and there is no argument for even for the existence of an upper bound. It's not clear. So the quadrupoles are also, multipolar structure can be extremely different from Kerr. All null or time-like geodesics also may possess a very complicated structure, very different from Kerr or Kerr-Newman. For Kerr, we have ergo region and ergosphere. Here, in some regions of the parameter space, we find ergosaturns. So there are some very specific features. Different shadows. This one is standard one from Kerr, but for such configurations, one could find disconnected shadows, multiple shadows for a single black object. And finally, I mentioned already, they possess a solitonic limit. So they reduce in the limit of vanishing horizon radius size to spinning particle-like object, this scalar or Proca stars. And I have a few slides about yet another recent development. Well, it was 5 years ago, so it's still recent. There is this fantastic work of East and Pretorius clarifying a long-standing problem about the endpoint of superradiant instability. They managed to implement a consistent numerical scheme for spin 1 and follow the evolution of some Proca perturbations, some Proca clouds around the Kerr black hole, taking into account back reaction. And if you follow they manage to keep the evolution for a long enough time, such that everything saturates, you reach some plateau, and the endpoints are indeed as expected by some of us, hairy black holes. In this case, Proca black holes with Kerr black holes with Proca hair. So in this diagram, for example, the small black points here are initial configurations taken by East and Pretorius with a tiny Proca perturbations. Then if you follow the evolution, it's almost conservative, as was mentioned already yesterday by Nuno, I think. And these red points are the final endpoints of this evolution, which indeed lie in the domain of existence of hairy black holes. So any evolution stops, and you reach a stationary configuration corresponding to a Kerr black hole with Prochy hair. So this is, it was the first dynamical counterexample to the no hair conjecture. It means hair can appear dynamically in realistic processes. It could be relevant to astrophysics. It's not just a simple mathematical exercise, if you like. And we had some discussions with a few people in the audience about this attempt to construct an analytical model for such configurations. At least in some regions of the parameter space, it is possible to come with some analytical estimates based on two very simple arguments by considering this kind of hairy black holes as a bound state between a horizon and some scalar or Prochy cloud. And then it is possible to derive some universality relations valid for such configurations. So the starting point is rather trivial. One splits the total mass and angular momentum, as usual, into a part which sits inside the black hole horizon, and the one in the field. This holds, for example, already for Kerr-Newman or Royston-Nordstrom. You have a part of the energy outside. Okay, and then we use two postulates, which are rather simple. Because of this picture of the bound state between a small horizon and some cloud outside, these are different scales. So we expect the horizon some of the horizon properties to be similar to what we know from Kerr solution, close to the horizon. So the relation between mass, angular momentum, and horizon area is similar to Kerr, but at the level of the horizon quantities, not ADM quantities. And then we are postulating a kind of first law at the level of the clouds, which holds indeed in the absence of the horizon. And using these two postulates together with some elementary mathematical manipulation of the algebraic manipulations, one can find some nice and simple enough analytical results which are expressed in terms of what we call hairiness parameter. So you are taking the ratio, for example, between mass stored in the field outside the horizon and the total mass, and the same for angular momentum. And well, if you are performing one computation, for example, you can find such exact relation between horizon area of a hairy black hole with some given mass and angular momentum as compared to the corresponding horizon area of a Kerr black hole with the same parameters. Extra parameter here is the mass, for example, of the scalar here. So it shows it's a kind of analytical proof that the hairy black holes, at least in this setting, are entropically favorite. They maximize the entropy for given global charges. And there are more analytical results. Anyway, so this is a comparison between numerical data when solving the system of equations numerically subject to some boundary conditions and these analytical estimates. And it works surprisingly well for some region of the parameter space. So that's beautiful. And now finally, let me advertise again. On some server in Aveiro, we provided numerical data and Mathematica files and with solutions. If you would like to cross-check independently, use this data, we are very happy. So they are publicly available on the server in Aveiro. Okay, so with that, I will finish this part. If there are questions now, we're at the end. Okay, now, so this, sorry. This was for Spinzero. And following the approach first lecture, let me mention that there are two main directions when discussing the subject of hairy black holes, discussing the status of this conjecture for more general matter fields, or changing the theory of gravity. Let's keep for the moment the first approach. We have seen the situation for Spinzero, scalar field, more or less. I have a few more comments after that. Still in Einstein gravity. What about spin 1? So black holes with vector fields. Here we have first Einstein-Maxwell, and we have seen there are a number of very rigorous uniqueness theorems. We have seen the case of Proca, which is still spin 1, but quite different from usual Maxwell. But let's go to non-abelian fields. So not simple Maxwell, but nonlinear gauge fields, which are very well motivated. In standard model, we have SU3 cross SU2, for example. In ground unified theories, we have SU5, SO10, and so on. What is the situation there? Is the same picture valid? The picture we know from Reisner-Nordstrom and Kerr-Newman? Well, for a few decades, this was the consensus. There are even some no-hair theorems in the literature proposed in the 70s, in the 80s. And everybody thought this is the case. There are some solutions with non-abelian fields, but they require always presence of scalars, or gauge scalars, like magnetic monopole, which was found in 74. But what about gauge fields alone? And it's quite interesting lesson, because if we have only gravity, then there are theorems, famous Lichnerovitz theorem. There are no gravitating solitons alone, gravity alone, in asymptotically flat case, 4 dimensions. Only black holes. Now, if you take Young-Mills alone, there are, again, a kind of no-go theorems, very rigorous, Coleman, Deser, showing the absence of solitons in 4 dimensions, asymptotically flat, and the Lorentzian signature. You have only instantons, but these are very different animals. So, and then for electrovacuum, we have these theorems, and everybody thought this is the case also for putting together when going to larger gauge groups. But it's interesting, if you go to nonlinear fields, as first realized by these authors in '88, it is possible to cancel these two opposite effects, the attraction of gravity with the repulsion of non-abelian fields. So this is extremely important. You need nonlinear fields, and they can balance attraction versus repulsion, and there are gravitating solitons in such models. So to answer one question, you need both ingredients, both gravity and Young-Mills. Any component alone is not enough. And it's a famous paper. They found, they provide numerical evidence for the existence of interesting family of gravitating solitons in this model for the gauge group SU2. And these solutions are regular everywhere. Soon after that, the mathematicians came with the existence proof, even uniqueness, and so on. And 2 years later, other people came with the hairy black holes. So you can put a tiny Schwarzschild black hole at the center, and they will survive. Such configurations are static and spherically symmetric. Later, they were generalized for rotation. It's quite complicated picture, in fact, because you have many degrees of freedom for non-abelian, more degrees of freedom than the simple U1 case. And this came as a big surprise. People took this time into account, this violation of the no-hair conjecture. It was the first clear violation of the no-hair conjecture, which resonated with the community. So people after that took seriously the possible existence of hairy black holes. And you can find a review here. But it's interesting because this was a forgotten paper, Sleeping Beauty. It was a result in '79 by some physicists finding exact solutions for Young-Mills fields in the background of Schwarzschild. But they are completely ignored for more than 1 decade. But it was clear the hairy black holes are there because you find at the probe limit an exact solution even for SU2 field. Okay, So that's the situation with non-abelian fields. I have few more technical slides, but perhaps it's going too technical. But this subject is quite complicated. Even the construction of a spherically symmetric ansatz for an SU2 field is more involved. You have more potentials. But in the end, you have to solve a set of ordinary differential equations subject to some boundary conditions. And it's interesting, at infinity, these are some profiles of the solutions. They have one index. There is no global charge. At infinity, everything is Schwarzschild. You don't have any extra charge. If they are non-abelian, that is not like Reister-Nordström or Kerr-Newman. There is no electric charge, no magnetic charge. They are completely neutral. So there is no imprint at infinity of their presence. There is just one integer corresponding number of nodes in the radial profile. And well, it's interesting mathematically that all these solutions were shown to be unstable first. Even worse, they didn't find so far, to my knowledge, any clear physical application. They are likely perhaps relevant even at the microscopic scale. These are, their mass is Planckian scale, so they are heavy for microscopic objects, but being unstable, perhaps early universe, there are speculations. And well, that they came as a first counterexample in any case. They are interesting historically, at least. Now, so this is a very brief review for Spinzero. So we have, for spin 1, a vector field, we have Proca and non-abelian fields. What about putting together spin 0 plus spin 1? One possible direction, simple enough, are the so-called Maxwell-Dilaton models. So, or if you prefer, Dilaton-Maxwell, spin 0, spin 1, with a specific coupling between the scalar field, which for historical reasons is called Dilaton, and the Maxwell field, it's exponential. We have seen yesterday in 2 talks, I think, this type of black holes in Melvin universe, for example. And they were generalized for young meals as well. So, and there are interesting exact solutions in this case, at least in the absence of rotation. You have a family of solutions. The scalar field, Dilaton, decays as 1 over R. But this is secondary here, because this parameter in the far, big D, capital D, in the far field expansion is not a new parameter. It is a function, complicated function of mass and electric charge. And for the existence of such configurations, you need an electric charge. Because of the Neuer theorems, you don't have zero, well, in the absence of electromagnetic field, it's just Einstein scalar field. And such Lagrangians, as mentioned already yesterday, have some motivation from, from string theory, Kaluza-Klein theories. This was an active area of research and provided yet another violation of the no-hair conjecture, but not really the spirit. So this Dilaton charge is just a function of mass and angular and the electric charge. Then can be generated via some symmetries from vacuum solutions or electrovacuum solutions. I have in mind these Harrison transformations. So in some sense, this is not a very convincing violation of the no-hair conjecture, but they are still interesting, and there is still work done on that. Okay. So let's summarize a bit the situation so far about violations of the Neuer conjecture. For spin 0, we have this clear violation in the for a complex massive scalar field. It's a physical model. For spin 1, we have for a U1 field the Kerr-Newman solution. Sometimes people used to say the electric charge is a kind of hair because when taking respect to Schwarzschild or Kerr. Then we have SU2, these Bartney-McKinnon type solutions, which are clear violations of the Neuer conjecture. By the way, they were generalized later to SUN, so the rank of the gauge group is not, dimension of the gauge group is not important. Then we have abelian proca, which is a cousin of complex scalar field. What about the case with spin 0 plus spin 1 in particular for gauge scalar fields? This is a very natural model because in standard model we have gauged fields. The Higgs field is gauged with respect to SU2 cross U1 in the electroweak sector. So yeah, it's another slide about the motivation. We will sit in between, putting together spin 0 and spin 1. Maxwell in the simplest case and complex scalar field. For Einstein scalar field, we have this boson stars. Let's discuss only spherically symmetric limit in this context, because otherwise the things will get quite complicated. So for the spherically symmetric sector, we take this theory. It has a global U1 invariance with some associated neutral charge. There we have the boson stars. In the spherically symmetric case, as I said, these hairy black holes do not exist. There are some no-hair theorems. They need rotation always, so we don't have spherically symmetric black holes. Now, we are localizing this interaction, making the symmetry locally. So we have some local U1 symmetry. You are gauging the complex scalar field, adding U1 Maxwell field. And this is more realistic, as I said. It can be viewed as appearing inside standard model, if you like. In the spirit of the standard model, you need a gauge coupling constant. And it's interesting because there are gauged boson stars. They were discussed by Yetzer and Van der Bay in the 90s for spherical symmetry. But the expectation, and there is even a no-hair theorem claiming there are no black holes. And this is a theorem given by Mayo and Bekenstein in 95, if I remember well. But it's interesting because this theorem, in fact, has a quite clean loophole. So even big people can miss some aspects. Indeed, there are two papers at least discussing the existence of static, spherically symmetric black holes for such a model. So again, this is a recent result. Rather than expected by the community working in this area, even a complex scalar field, gauged complex scalar field model may allow for spherically symmetric hairy black holes. They do not bifurcate from Reister-Nordstrom or Schwarzschild. They are isolated. And one aspect which is not fully understood, they require scalar field self-interaction. So that's the situation. And for more details, I refer to these two papers that at least their existence is clear. They have quite an expected pattern. Okay, so let's go now to more to real physics. So this is the Lagrangian of the standard model. We have seen it last month in the last talk. These are the fields in the nature. For spin 0, it's Higgs. Then we have U1 and SU2. This is the electroweak sector. Now, what about black holes inside this Lagrangian? When minimally coupling the Lagrangian of the standard model with Einstein gravity. And indeed, one can construct rigorously solutions of Einstein gravity with matter fields given by the Lagrangian of the standard model, setting the fermions to 0. This is an important point. Just the bosonic content, and taking the full Lagrangian usual gauge derivative, taking into account both SU2 and U1, with the true numbers in the numbers from experiments for all coupling constants. First, for the standard model, we have the sphalerons, which were found in the 90s, Klinkhammer and Manton, and I don't put details because it's quite complicated. They are very long expressions and not so transparent, but the solutions are there. It's a clean violation of the no-hair conjecture, and the same holds for, by the way, for magnetic monopoles, which appear in extensions of the standard model, or in this Georgi Glashow version with a triplet Higgs field. I recall that in standard model we have complex doublet of scalars, so 4 scalars without any constraint. And but the picture is quite similar in both cases. It's the mechanism I mentioned during the previous lecture. You have configurations without gravity, just in flat space-time, like magnetic monopoles. I have in mind these Toff Polyakov magnetic monopoles with non-abelian gauge fields, which are solitons, regular, no singularities. And then you take into account the back reaction. They will curve the geometry, but they are not terribly heavy, so this curvature are really small. So the mass for a sphaleron is around 10 TeV, for example. And then you can add a black hole at the center. This black hole can be Schwarzschild-like, but there are extensions also including rotation. So that's the mechanism. About stability, the sphalerons are unstable already in flat space-time without gravity. The monopoles, some of them are stable. So more or less, that is the emerging picture. Sorry. Okay. So this concludes somehow the first part. Yeah, as I said, there are two possible directions, just to include more and more matter fields and see if there are hairy black holes or not, keeping Einstein gravity, or changing the model of gravity, eventually take into account the existence of extra matter fields together, but with a non-standard coupling with gravity. Now let's go to this second option. So Einstein equations will get more complicated. And simplest classical, so we call this part hairy black holes beyond general relativity, because the model of gravity will be more general. And let's start with this classic example of Einstein Gauss-Bonnet dilaton models. They were proposed long ago, I think already in the 60s at least. This kind of Lagrangians, there is some motivation. You find the first Gauss-Bonnet term coupled with some scalar in heterotic string theory in 10 dimensions. First alpha prime correction. And then there are other reasons, so it's reasonably motivated. So in this case, you have Einstein gravity term, a real scalar field with a non-standard coupling with the Gauss-Bonnet curvature invariant. Gauss-Bonnet alone in 4 dimensions is topologically invariant. It will not contribute to the equations of motion, but due to the coupling with matter fields, here with a scalar, it becomes dynamical. So it changes the equations, but it's interesting because the equations of motion are still second order, which is important. But although what we learned very recent, they seem to possess some pathologies. In the some generic features, they may lose hyperbolosity because of these extra nonlinearities. But at least formally and for elliptic equations, the system of equations is very simple. Well, it's not. It's here. You can see there are still second-order equations, and the scalar field equation gets a source, and which allows to circumvent the no-hair theorems for scalar field. So these Bekenstein arguments we have seen during the last lecture is violated via this coupling. For dilaton, again, people call this scalar dilaton for historical reasons. It's an exponential coupling, but as we shall see, you can consider more general couplings between the scalar field and the Gauss-Bonnet invariant. And there are many interesting features, many interesting papers. There are generalization of Schwarzschild black hole first with such hair. An interesting feature here, and rather counterintuitive, is the existence of a minimal size of the black hole. such Schwarzschild can be set to 0 size, then you approach Minkowski spacetime, black hole disappears, but not in such models. There is a minimal size of the black hole because you have a new coupling constant, which is with alpha or alpha prime sometimes with dimension of length square. The Kerr bound can be violated, but not very dramatic. There are only tiny violations. And also there are no solitons here, or at least not known so far. Okay, so then we have, this is somehow the picture. If you take the ratio between the dilaton charge, this extra quantity in the far field expansion of the scalar field, it's a kind of scalar monopole charge, if you like, versus mass of the black hole, and you compare with the size of the black hole, there is some non-uniqueness. The picture is always the same. Expect some large values of this coupling constant in the parameter. And for example, from here, one can see the existence of some minimal size of the black hole horizon. So, and here again, there are no analytical results. No exact solution, in fact, and but one can do analytical studies to some extent. The situation is still reasonable, different from our case, at least in the spherically symmetric, for a spherically symmetric black hole. And now there is a Chasm model, this so-called Chern-Simons modified gravity, which took the attention of the community for last few decades. In 4 dimensions, you have 2 different topological invariants, so total derivatives built in terms of the metric functions. It's Gauss-Bonnet invariant, R square, people call it normally, previous slides, or this Chern-Simons invariant, which is a product between an R and R dual, 2 Riemann functions. And you make it again dynamical coupling with a scalar field. And these are, in some sense, counterparts of the Gauss-Bonnet black holes, but it's mathematically a rich subject because Schwarzschild is not a solution. You need always rotation. It's an interesting subject. The equations of motion here are 3rd order, even for elliptic problems. Solving them non-perturbatively is a challenge. There are a number of perturbative results. So this is a different class of hairy black holes which do not possess, well, in the static limit, you have only GR. But once you include rotation, for Kerr black holes, you may have such corrections from this direction. And such a term has indeed, again, some motivation based on string theory, some version of the string theory. Now, well, let me briefly mention, this will be mainly the subject of next talk on Friday, but there is a generalization. It's a subject which enjoy recently considerable interest. Different type of violation of the Neuer conjecture based on black hole scalarization. And here, basically, what we are doing, we are more liberal with the models. The coupling between scalar fields, for example, and gravity, or even with the matter fields. We are going beyond the standard couplings. And you find a different type of violation from a different direction of all these Neuer theorems. So in some sense, we are circumventing the Neuer theorems by violating the first assumption. They possess a non-standard coupling between matter fields, scalar field in particular, and the curvature invariance. So I think I better stop here. And time for questions, please.
So thank you, Eugen, for this second part of your short course. So I hear that there is already a question online. So can you please unmute yourself and ask the question?
So, hi, can you hear me?
Hello. Yes.
So first of all, thank you for your interesting lecture. you showed some hair black hole solution from Einstein-Maxwell scalar model, right? Which was obtained using something called a resonance condition. So maybe I missed something.
I did not
what is
have
this
time
resonance
to.
condition?
Yes, thank you very much. It's a good question. I did not have time to come with details. It's interesting for this synchronized black holes, Kerr black hole with rotation. There is a condition putting together frequency of the field and angular velocity at the horizon, omega h, yeah? Now, for this class of black holes with gauged scalar hair, there is still something similar related again with superradiance. You find a condition between frequency of the field, so we are using again a complex scalar field, and this time it should equal the scalar, the gauge potential at the horizon multiplied with gauge coupling constant. So it's very similar to condition of zero imaginary part when taking the resonance condition for this charged clouds in Reisner Nostro background. It's in the same spirit. That this comes mathematically because they do not bifurcate from a zero mode this time, but it's a condition which assures the regularity of the solution at the horizon. In fact, even for Kerr black hole, if you consider other space-time dimensions or different asymptotics, it turns out that the resonance condition, the synchronization condition between frequency and the parameters of the black hole is more fundamental, is not necessarily related with the existence of these scalar clouds with the superradiant instability. And this is the case for gauge scalar field. We have a similar condition putting together frequency and this electrostatic potential at the horizon, Q over RH, if you like, for Reisner Nostrum. Did I answer your question?
You.
So that's, yeah, indeed. It's a mathematical result.
Okay, thank you. Are there any more questions online? Well, let's go to the audience there. Are there some questions? Okay, I see two. Let's try to go roll the first. Yeah, it was almost exactly the same time, so you're closer. So
okay, thank you. Thank you, Professor Eugen, for the very nice lecture. My question is about the circularity properties of all these models. Essentially, circularity is a Frobenius integrability condition, and you can write in terms of the curvature tensor, and then after that, the stress energy tensor using the field equations. So I remember that the standard scalar model, Einstein and Clay-Gordon system, satisfies this circularity condition. So the circular ansatz for the metric is the most general, so you don't need the non-circular. But how about these other models? So are all they circular or not?
Okay, so there is a first remark, if you don't mind. It's, in my opinion, there is a simple way to look at the circularity condition. It's just a consistency of the ansatz. If you get for a given matter ansatz that some components, extra diagonal components like R phi, RT, so on of the energy momentum tensor are zero from the very beginning because of the ansatz, then it is consistent to use a metric ansatz which gives you zero Einstein equations, yeah? So 0 equals 0. And this is the case. We check it explicitly for all models discussed here. And more and way or another for all models in the literature, there is a paper by Mudon group, I know, but there are some approximations. No, there is a known case where the circularity is violated for these young mills. If you Yes, but they done only at the probe limit in flat space, and the most general ansatz will violate the circularity condition. But nobody tried to construct really numerically such solutions. Yeah, thank you for the question. So you have these extra components of the energy momentum tensor excited, and usual metric ansatz will not be enough.
Okay. Yeah. Do you have another question?
Because this Einstein-Young Mills is a total mess, even for the spherically symmetric case.
Already for the spherically symmetric case,
yes,
it's...
someone tried to put a non-circular ansatz in this...
They found, it's quite a straightforward computation on the paper. There is an ansatz, general ansatz, with these extra components of the energy momentum tensor are non-zero. And you can even excite this ansatz in flat space. But at the level of gravity, I'm not aware of any work of back reacting.
Okay, thank you very much.
Okay, thank you, Haroldo. Next question, João.
So, first of all, thank you for your lecture. My question is concerned with the Einstein-Chasm model that you showed, namely the limit for the small black hole, the black holes having a limit, and if these solutions have zero temperature. Are you aware of that?
I do not recall very well, maybe George, but I would think it's not zero temperature. If I remember well.
So are there any studies concerning Hawking radiation in those spacetimes?
Oh, yeah.
Oh, okay.
Yes, please.
So if I may, no, at the critical solution, the Hawking temperature does not go to zero. There's a non-vanishing value for the Hawking temperature. What happens there is that there's an equal singularity that starts to develop outside of the horizon. Something like
this
that.
Was for Hordensky, but since this is a, no?
Yeah, this was, I studied this with Pedro Fernandes in Queens, Mary Queens. And we saw that for the little tonic and the shift symmetric case, that was the case.
The same, yeah.
There's a critical solution where the Hawking temperature does not go to zero, and there's a singularity that starts to develop outside of the horizon.
That's a singular limit anyway. Mm-hmm. And indeed, there is quite a lot of work about thermodynamical properties. Yeah, it was a active, topic in the 90s, beginning of 2000. People studied the spherically symmetric black holes in such models from various directions. And they have some interesting thermodynamical properties. For example, Schwarzschild is thermodynamically unstable. Here you find a branch, if I remember well, which Gauss-Bonnet corrections could stabilize thermodynamically. You get a positive specific hit. There are some...
So thank you, João. Were there any other questions? I thought I saw... Yes, Caio.
So this is about the charged scalar field case that you mentioned, that for spherically symmetric black hole in the gauge scalar field, which you have electromagnetic field plus a scalar, you do have a hairy solution. I think I remember that I found it, but can you comment a bit more about the difference between? So you mentioned that these black holes that are formed inside the scalar field configuration, they are not similar to Horizon-Awesome. They are different from the Horizon-Awesome case. How do you describe this?
Non-perturbative. Yeah, it works. Yeah, it's. Well, at least for me, this result came as a surprise. There were some no-go results, but always, if you look careful enough, there are loopholes. So first, you don't have these clouds. For Einstein nostrum asymptotically flat, 4 dimensions, you don't have this normalizable zero modes similar to Kerr. So they don't bifurcate from Einstein nostrum. They form a branch of solutions completely disconnected from electrovacuum. And that perhaps made their construction so challenging, because you do not have a no limit.
Yeah,
but they are recovered by different groups. Then they are connected, however, in some limits for some range of the coupling constants to charged boson stars, spherically symmetric, but you have to satisfy this resonance condition. Yeah. So you have 2 parameters for a boson, no, for these black holes, horizon radius and frequency, which is related to electrostatic potential. And then when setting to 0, in some limits you find a boson star. So this limit is known. You have always an electric charge, so they don't bifurcate from Schwarzschild as well.
But asymptotically, they must go to Heisen-Ostrom-like, right? Because
Heisen-Ostrom, yes. You have some corrections, but indeed, they have two global charges, mass and the electric charge, which equals the Noether charge. Its Noether charge gets localized in this case, yes. Yes, so there are, if you like, kind of Heisen-Ostrom is some nonlinear dressing with scalar hair. But what I find surprisingly in this moment, and we don't really understand, you still need this self-interaction. Apparently, in absence of self-interactions, different from Kerr, solutions do not exist.
Well, if it's fast, it's okay, but we are starting to get short on time. So we can perhaps continue this discussion afterwards. So let's thank the speaker again.